Hey team, welcome back. It's version 2 of a type of problem that you might find when encountering shear moment diagrams, okay? And this one is called the equation method. The last one that we did, the last video that we had was the graphic method. And so this is a little bit different. Students fear this one, okay? But it's not too bad. But let me see if I can help you solve this problem, okay? So we need to draw the shear moment diagram for this thing here, okay? This weird beam. Has kind of a trapezoid load or something weird on it, okay? Here's how you do it. Number one, step one. Guess what? Find global equilibrium. Okay, find global equilibrium, just like before. So what do we have here? We have a beam. Okay, we have a roller over here. We'll call this AY. We have a pin connection on this side. So we have a BY. And we also have a BX. But there are no forces in the X direction. So BX, he's 0. Okay. Now what I'm going to do is I'm going to take this distributed load and I'm going to break it into two parts. And I'm going to call it a rectangle with a triangle sitting on top of it, right? And so if I look at converting that into a concentrated load, right, the rectangle portion would be here, and the triangle portion is going to be over here somewhere, right? Okay, because the centroid of a triangle is at 2/3 the base. Whoop. The centroid of the rectangle is right in the middle. So over here on this guy, I have this, which is the rectangle. And how big is the rectangle? It's 3 by 3. That's 9. And then over here, whoop, I have the triangle. And how big is the triangle? Well, it's 6 tall, 1/2 base times height, right? 6 times 3 is 18 divided by 2. Oh, that's 9 also, isn't it? Let's make it the same height. Okay? And so from the middle, right, from the middle, where the triangle starts, this distance here, 1.5 meters. This distance here, 2 meters, okay? Right? Because the rectangle is at the center, which is half of the 3, and the triangle is at 2/3 the base, which is at 2, okay? So I think I got you here, don't I? Okay, sum the moments at A. This being positive. I'm kind of going fast because this should be an old statics review for us, right? So here we go. We got negative 9 times 3 plus 1.5 is 4.5 minus 9 times 3 plus 2, which is 5, plus BY rotates me positive, so BY times 6, right? Okay, how much is that? Well, that is 9 times 4.5 plus 9 times 5 equals 85.5 and then divided by 6. How about 14.25? And then, I'm sorry, that's not BY, is it? No, it is BY. So what does that make AY equal to? What does that make this guy equal to? Up stuff has to equal the down stuff. I've got 18 going down, so minus 18 makes AY 3.75. Right? AY plus BY equals up stuff equals the down stuff, okay? So let's take and put that stuff that we just found, let's put that over here. So this guy at BY is 14.25. And then this guy over here at A is 3.75. Okay. You know what? We're ready to graph this thing. We got our global equilibrium. Let's go. All right. So I'm going to put my little deal in here. Okay. here comes the V diagram. And V is in kilonewtons this time. And if this stuff is confusing to you, you go back to the static series and watch this stuff on statics, because I have this as there additional problems for you, okay? So here we go. This is the M diagram, and that one's in kilonewton meters, okay? So, and then we put in our discontinuities. I think something interesting is happening right here. And I think something interesting is going to happen right there. Okay? Whoop. Whoa. Okay. So what I'm going to do, I'm going to erase this global equilibrium so I can give myself room, because I think I'm going to need it here in just a second. Okay? Anyway, I got the numbers that we found written on our diagram over here, right? Okay? All right, here we go. So the V diagram is going to be easy, right? It's going to be real easy. And it'll just be the graphic method, just like we always done. It's super easy, okay? So here I am. Let's get my blue pen. Let's do it in blue. Blue. Okay? So I start off here. Remember, we got our load backpack on. The first thing that we're going to do, whoop, jump up 3.75, okay? 3.75. There we are. Now what? We start walking along. No change, no change, no change. Bam. Uh-oh. Now what? Okay. I know that I have to go down 18, right? I have to go down 18. And so you can do this, right? In your calculator, because this was 9 and that's 9. So that a total accumulated load is 18, isn't it? So I'm at 3.75, 3.75. If I subtract 18 from that, right? 3.75 minus 18 takes me down to where? Negative 14.25. Isn't that handy dandy? Okay? Because we got a John Denver force over there, don't we? Okay? So how do I get from here to there? You tell me, how do I get there? You got it, right? Slow, then fast, right? This is, I'm accumulating load over here. Short stacks, fat stacks. So slow, then fast. So slow, then fast looks like this. Slow, then fast, okay? Something like that. And then what? Bam, I'm at 0. I mean at negative 4, and this is negative 14.25. John Denver force, boom, take me home, baby. Right up to 0, right? Take me home to the place. You know the song. You know the song, okay? So there's my V diagram. I know you're like, equation method. Pfft, this looks like every other one. This is easy, right? Okay, when do I use the equation method? Only one time. One case. Okay? And that is this. When the V diagram crosses the axis with a parabolic curve. Okay? The only time, one case, when the V diagram crosses the axis, the V diagram crosses the axis right there, right, with a parabolic curve. We got that case, don't we? Then you got to use the equation method, okay? That's the only time. Every other time, you can watch the last video. You can just use the graphic method, which I love and is nice and easy. But this is the one case that gets a little funky, okay? So what are we going to do? Well, here's what I think we should do. We need to find this point right here, right there, where that thing crosses the axis, right? Because now this curve down here, I mean, all day long, I can construct the curve. That's easy, okay? A plus, a minus, right? So this thing is going to go, this graph down here is going to go uphill, uphill, and then downhill, right? So it's going to go uphill a slope, right? Because the order of the lines, right? I have a flat, so the next graph down is going to be a slope. Sloping straight uphill. Then I'm going to go uphill a little bit more. And how am I going to slope? That's parabolic. It's going to be cubic. It's the same shape curve. How do I get there? Fast, then slow. So it's going to go like this. Okay. And then I'm going to go downhill, slow, then fast. And I know I always go back to 0. That's, Dr. Hansen told me that. Slow, then fast. And so there you go. Boom. There's the graph. Done. Do we get 100 for that? Well, probably not. Okay. Because what do you, as an engineer, right, if you're going to have to design that beam, what are you worried about? You're really worried about what is the bending moment at that point right there, okay? So I know the shape, but I don't know the value. That's what I need to find. I need an equation for M so I can find that value right there. And I'm going to show you how to do it. Here we go. What you do is we're going to cut this beam. We're going to say, hey, this is a distance X. Okay? Now, the one I did in the statics video, I did from this side going X was this way. But I think it's easier this time if I use X from that side. I can do whatever I want because I'm the king, right? Okay. So what I'm going to do is I'm going to cut the beam right there. Whatcha? Okay? I'm going to cut that beam in half. And I'm going to draw that little free body diagram, and it looks like this. Okay? This is a distance X. Okay? That's the distance X. And what do I have going on here? I have 14.25. I have a distributed load that looks like this. I know that the load on this side over here is 9 kilonewtons per meter, so I know that. 9 kilonewtons per meter. And then what happens when you cut a beam? You must have a... that's the one. N, V, and an M, right? So there's our M, N, and V, our internal forces where we cut that beam in half, all right? So all you got to do is a little old statics problem on this. But one of the things that I need to know is this. How tall is that curve right there? Okay. Well, what I'm going to do is I'm going to make this my origin, okay? This is my X, Y, okay? You can pick it anywhere, but I think this makes it a little bit easier for me, okay? What's the Y value right here? Gosh, if we could only write an equation for the slope of that line. Hold on, we can, can't we? Y equals, okay? Is that a positive slope or a negative slope? Whoop, that's a positive slope, isn't it? And the positive slope is rise, which is 6, over run, which is 3. So 6 over 3 times X, and then what? Where's the Y-intercept? Plus 9, okay? Plus 9. That's the slope of that line. But what's the height over here, okay? Now I made that my origin, which made this up here my Y-intercept, doesn't it? So what's the height of Y over here? Well, you know what I'm going to do? I'm going to put a negative X in for X, right? So the height of the curve over here is going to be this. It's going to be this. Y is equal to, I'm putting a negative X in there, 9 minus 6 over 3 is 2, isn't it? 2x. Okay? I'll put a negative in there, which makes this thing here negative, which, there you go, there's the negative, okay? So now I'm all good. Okay? So let's do this. What do we have here? Let's write an equation for V. Okay, so I have two shapes here. Right? I have a rectangle and I have a triangle sitting on top of it. Okay? So how big is the load that the rectangle is? This part right here is how big? Well, it's base times height. There's the base. It's X. There's the height. So this guy, this area here is 9x minus 2x squared. Wait, what? I just multiplied x times that height. That's all it is. So there's an x there and another x there, right? Well, how big is this over here? This is 1/2 the base times the height. Oh, the height is 9. No, the height is not 9. The height is 9 minus that over there. 9 minus 2x. Okay? How do I get rid of those parentheses? Now, notice what I did. I put that 9 minus that whole thing, right? So I put it in parentheses. So to get rid of the parentheses, I'm going to distribute the negative. So that one becomes a positive, doesn't it? Okay? And what does this simplify to down to? 9 minus 9, that goes away. So this up here turns into, oh, the 2's go away. This turns into x squared, doesn't it? Okay? That whole area of that triangle is x squared. Well, that's pretty cool. All right, so from this free body diagram, let's write the sum of the forces in the y and see what that gives us here, okay? So here's what we get. We got a plus v, right? And remember, the v is just an assumed direction. We're using the positive sign convention. It might be the other way, okay? Plus v plus 14.25, okay? And then what else? Minus this bit, right? Because I've got a downward force here and a downward force there. So minus the x squared part, and then minus this guy, minus 9x minus 2x squared. And I'm going to put that in parentheses, right? Because it's minus that whole part there, okay? Now I can come back and distribute that negative, which is going to turn that to a negative and that into a positive, which makes v equal to, let's move some stuff around, right? I got to move everything to the other side. So x squared, when it gets moved to the other side, is going to become positive x squared. Let's see, and then minus 2x squared, right? And then this is going to be plus 9x. And then this is going to be minus 14.25. Okay? And these first two will simplify, and so v is equal to what? V is equal to minus x squared plus 9x minus 14.25. Okay? So there is an equation for v. Okay? And like I said, I assume the direction of v. If it was going the other way, what would happen? Well, all of these signs would just change. That's all. Okay? So now let's do this. Let's do the sum of the moments about this point right here, about the cut, okay? I'll call it x for where we cut it, okay? And what do we get? Well, we have m. Again, it's an assumed direction, but that's negative. So minus m, okay? And then what? I've got this guy right here, which rotates me minus. So that's that. That's minus 9x minus 2x squared, right? Times how far away? X over 2. Okay? And then I've got this guy, which is just x squared, which also rotates me negative. So minus x squared times how far away? Well, this whole thing is x, but that's at the centroid of the triangle, so it's 2/3 of x. Okay, and then I've got the 14.25, which rotates me positive, so plus 14.25 times how far away? X. Okay, so can we simplify that any? Yes. Let's simplify that sum. I'm going to do a little erasing here. Okay, I'm going to come up here. I'm going to erase my one case. Okay. And let's see what that turns into. That turns into m is equal to, all right, let's do a little distributing here. So this is going to be, I'm going to still leave that negative there. So I'm going to do this little inside, which would be 9x squared over 2 minus what? Minus 2. The 2's cancel out, x cubed, right? Okay. Minus x cubed, and then this guy turns into what? Minus, that guy over there is minus 2/3 x cubed. And then this guy over here is just 14.25x. Okay, now I'm going to get rid of these parentheses by distributing it negative. So that becomes negative, that becomes positive. And let's see, what is a 2/3 or 1 x cubed minus 2/3 of an x cubed leaves you with 1/3 x cubed, right? So m is equal to 1/3 x cubed minus 9x squared over 2 plus 14.25x. Okay, so there is an equation for m. Okay, now I wonder what this x is here. I wonder what x is. You know what? V here at some distance x, right? At some distance x, what does v equal? V equals 0, doesn't it? So let's just take this equation here and rewrite that, and that equation will look like this. 0 is equal to, this one down here was equal to 0 too, right? Okay, 0 was equal to, I'm just going to move all this stuff to the other side of the 0, right? So x squared minus 9x plus 14.25, okay? Now what does that look like? That looks like a quadratic equation to me, right? And so let's go to, we have a quadratic equation solver on here, second polysolve. And so A is going to be 1, B is going to be -9, and C is going to be 14.25. Solve, and we get x could be equal to 2.05, or, let's see what else, the other root it gave me is 6.95. Okay, so one of those is going to be correct, and one of them is going to make no sense whatsoever. Well, if x is 6.95, where does that put me? That puts me like over here off the beam, right? That cannot be true. So this one, no good. And so the one I want here for x is 2.05, okay? So x equals 2.05. Now I should be able to put 2.05 in here for x in this equation, and what should it give me? 0. It should give me 0, and it does. Okay, so let's go up here, because what I'm after is this value of m right here. What is that guy? Well, let's put 2.05 in that equation, and let's see what we get. Okay, so here we go. Clear, 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 clear. Enter, 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 clear. Good lordy. Okay, we get 2.05 cubed divided by 3 equals, and then from that subtract 9 times 2.05 squared, and then divided by 2, that equals, and then from that add to that 14.25 times 2.05 equals 13.17. So that's what m is equal to, okay? When I put 2.05 into that equation, I get 13.17. So this value right here, 13.17. You know what? How could I check that? You know what I know for sure is this. I know that this area right here from the graphic method, right? The graphic method tells me that this area is 3.75 times 3, 3.75, good night. 3.75 times 3 is 11.25. So that tells me that this guy right here is 11.25. So how could I check that? Well, I could put 3 into this equation. Put 3 in for x and x and x and see what it gives you. And you know what? It gives you 11.25. Okay? So that way I can kind of confirm that my equation is right. Now this is way harder than the word I worked back in statics. So if this is a brain twister for you, rightly so, this is quite a challenging little problem. So I hope this makes sense. This has been the equation method, and I'll see you next time.